How did the Romans manage to build a structure capable of accommodating the entire population of a city? And more importantly, how did they manage to let 50,000 people in and out in a matter of minutes without crowding, chaos, or panic? We are accustomed to admiring the Colosseum for its size and architecture. But its true genius lies not in the arena or the gladiators. The real marvel is the system that controlled the flow of people with the precision of a mechanism. For the Romans, the problem was not simply to build a huge structure, but to make it safe. Thousands of people had to enter and exit at the same time, take their seats without confusion, find passageways, and navigate a giant stone labyrinth. And all this without modern technology, without sensors, without evacuation plans, and without electronic turnstiles. They created a network of corridors, staircases, and exits that works so efficiently that modern engineers are still studying its principles. Watch the video to the end, and you will learn how Roman builders solved the problem of crowd movement 2,000 years before the advent of computers, why the vomitoria system was a revolution of its time, and how ancient engineers laid the foundations on which every stadium in the world is designed today. What if I told you that the Colosseum was not built for entertainment, but as the most ingenious tool of social control in history? This gigantic amphitheater, built by the Flavian dynasty, was first and foremost a political statement. It was a gift to the people of Rome after Nero's turbulent reign, a way to consolidate new power and ensure the loyalty of the masses. The policy of bread and circuses required not only food, but also a grand venue for performances that could accommodate everyone. The architecture of the amphitheater was a direct reflection of Roman society. The building was not just a gathering place, but a living map of the social hierarchy. Every resident of Rome, from senators to the poor, was assigned a strictly defined place. This division was not accidental, but carefully thought out and built into the very structure of the building. The system of entrances, staircases, and corridors was designed so that different social classes would never intersect. From an engineering point of view, the main task was not simply to build high walls, but to ensure unhindered access for tens of thousands of people. Engineers had to guarantee that crowds could fill and leave the building quickly and without panic. Any error in calculating the flow of people could lead to a stampede and disaster. Therefore, crowd control became a central design task. The very idea of accommodating 50,000 people in one place was revolutionary. No building before it had faced such logistical challenges. Roman engineers could not rely on previous experience. They had to invent solutions from scratch. They approached the problem with mathematical precision, treating people as flows that needed to be directed and separated. Therefore, when we look at the Colosseum, we should see not only an arena, but also a complex control mechanism. Every corridor, every passageway, and every staircase was part of a unified system. This system was designed to ensure order, safety, and, most importantly, the stability of the social structure. People came for the spectacle, but the building itself constantly reminded them of their place in the world. The genius of the Flavians' design was that they disguised this social control as concern for comfort. Each citizen was given a ticket, or Tessera, indicating their sector, row, and seat. This created the illusion of order and personal attention, when in fact the system simply sorted people efficiently. Each spectator was directed to their seat along a strictly defined route. These routes were completely isolated from each other. A senator entering through his special passageway could not physically encounter a craftsman climbing the public staircase. This invisible segregation was the key to stability within the amphitheater. The building itself prevented any possible conflicts or mixing of classes. It could be said that the amphitheater was a microcosm of Rome as a whole. It demonstrated the power of the emperor, who was able to gather the entire city in one place. It reinforced social differences, making them visible and physically tangible. And it showcased the engineering prowess of a civilization capable of solving problems on a scale never seen before. This need for control and order gave rise to the very engineering solutions we are studying today. The circular corridors and exit system were created not only for speed, but also for segregation. Crowd safety was important, but maintaining hierarchy was no less a priority for the construction clients. Thus, the history of amphitheater construction is not only a history of architecture, but also of social engineering. The tools they developed proved so effective that they outlived the empire itself. Understanding this dual purpose allows us to take a fresh look at the ruins that seem to us to be simply a place of entertainment. I'm very interested to hear your point of view. Was this system a brilliant engineering solution or a frightening tool of segregation? Write about it in the comments. And be sure to subscribe to the channel so you don't miss new episodes. Are you ready to learn the truth about the eternal material that made it possible to build these gigantic structures? Before engineers could think about corridors and staircases, they had to solve a fundamental problem. The Colosseum, for example, was built on the site of a drained artificial lake that was part of Nero's Golden House. This marshy, unstable soil was a nightmare for any builder. To solve this problem, the Romans undertook unprecedented earthworks. They dug a huge pit and laid an oval-shaped foundation several meters deep. This foundation was not made of simple stone, but of a new revolutionary material, Roman concrete, or opus cementicum. It was this material that was the key to the entire Roman architectural marvel. Roman concrete was not like modern concrete. Its secret ingredient was volcanic ash, called pozzolana, which was mined near Vesuvius. When mixed with lime and water, this ash reacted chemically, creating an incredibly strong and, most importantly, water-resistant mortar. This concrete could even set underwater, which was ideal for marshy terrain. The foundation of the Colosseum was a giant concrete ring 13 meters thick. This massive base distributed the weight of the building over a large area, preventing it from sinking into the soft ground. In essence, the entire amphitheater stands on a giant artificial slab created by the engineering genius of the Romans. Once the foundation was ready, the construction of the frame began. And here again, concrete came into play. The Romans realized that concrete could be poured into wooden forms, creating structures of any shape. This allowed them to quickly and cheaply erect load-bearing walls, arches, and vaults. Stone blocks, such as travertine, were used mainly for exterior cladding and for support points that bore the main load. It was concrete that made it possible to create the complex internal structure of the amphitheater. All those countless corridors and staircases that we are about to explore would have been impossible using traditional stone masonry. Concrete arches and vaulted ceilings created strong and spacious passageways capable of supporting the weight of tens of thousands of people above them. The elliptical shape of the amphitheater was also not a random choice. Unlike the Greek theater, which was built into the slope of a hill, the amphitheater was a completely freestanding building. The oval shape provided a perfect view of the arena from almost any point. It was also more dynamic than a simple circle and better suited for the spectacles that were held there. The construction of such a structure required not only ingenious materials, but also flawless logistics. The stone for cladding, travertine, was quarried in Tivoli and transported to Rome. Thousands of workers, both free craftsmen and slaves, labored on the construction site. The entire operation was like managing an army. Concrete structures allowed the Romans to build faster, higher, and stronger than anyone before them. They created not just walls, but monolithic structures. The arches of the ring corridors were, in fact, integral with the vertical supports. This gave the building incredible seismic stability and durability. Thus, before managing crowds, the Romans learned to manage materials. Their concrete became the foundation on which not only architecture grew, but also the entire flow management system. Without this durable, flexible, and fast-working material, amphitheaters for 50,000 people would have remained an impossible dream. But concrete was only a durable shell. The real genius lay in the internal logistics, in a system so perfect that we still haven't come up with anything better. Ready to learn the secret of the Roman vomitoria? I will reveal the most closely guarded secret of Roman engineers, a system that allowed 50,000 people to be ejected from a building in 5 minutes. At the heart of the entire crowd control system in the Roman amphitheater was an ingenious invention called the vomitorium. This Latin word comes from the verb vomere, which means to vomit or to spew. And this name perfectly describes their function. Vomitoria are not the exits from the building, as is often thought, but passages that led from the inner ring corridors to the spectator seats. These were wide, vaulted tunnels that penetrated the entire thickness of the spectator rows. They were designed to quickly and efficiently eject people to their sectors. There were 76 public vomitoria in the Colosseum, evenly distributed around the perimeter. Each of these entrances was numbered. Spectators received a ticket, a Tessera, which indicated the number of their vomitorium. This was the first stage of crowd sorting. People were immediately directed to their entrance instead of gathering in one place. Upon entering their numbered passageway, spectators did not immediately arrive at their seats, but rather entered a complex system of internal corridors and staircases. The vomitoria were designed with a slight upward slope, which intuitively slowed down the incoming crowd and accelerated the outgoing one. The width of the aisles was carefully calculated to avoid bottlenecks. The genius of the system lay in its decentralization. Instead of one or more giant entrances, the Romans created dozens of small independent channels. Each vomitorium served only its own small sector of spectator seats. This meant that the flows of people hardly ever crossed paths. This system worked equally well for both entry and exit. At the end of the spectacle, the huge crowd did not rush to a few exits, but naturally spread out across dozens of vomitoria. The passages that had spewed people into their seats now sucked them back into the inner corridors. The calculations of Roman engineers were remarkably accurate. Modern simulations show that the Colosseum could be completely evacuated in just 15 to 20 minutes, and in an emergency, possibly even faster. These are figures that many modern sports arenas would envy. The design of the vomitoria was thought out down to the smallest detail. Vaulted concrete ceilings provided strength, and smooth walls prevented the crowd from getting caught or slowing down. Lighting was provided either by openings to the outside or by oil lamps placed in niches. This system was not only effective but also safe. By dividing the crowd into dozens of small, controllable streams, engineers prevented panic and stampedes. Each spectator intuitively understood where to go, following the flow in their vomitorium. Today, we use the same principle. When you go to a stadium and look for your Sector A or Entrance 5, you are using a system invented by the Romans 2,000 years ago. The vomitorium is not just an architectural element. It is a fundamental concept for managing large crowds of people. If you like how we reveal the engineering secrets of the past, please like this video and be sure to subscribe to the channel so you don't miss new videos about the history of ancient Rome. What if everything you were taught about stadiums was invented 2,000 years ago in Rome? Upon entering through a numbered vomitorium, spectators did not immediately find themselves on the stairs leading to their seats. First, they found themselves in another key part of the system, the ring corridor. These corridors, also known as annular, from the Latin annulus, meaning ring, were the main horizontal arteries of the building. Imagine the amphitheater as a multi-story building. On each floor, a wide, vaulted corridor ran around the entire perimeter. These corridors were annular. They encircled the arena like rings on a tree trunk. Their main purpose was the quick and unhindered horizontal distribution of spectators. The system worked like this. You entered through the vomitorium arch on the first floor and found yourself in the first ring corridor. From there, you could go right or left to find the staircase leading to your specific sector. If your seat was on the second tier, you first climbed the stairs to the second floor and entered the second circular corridor. These corridors were incredibly important for preventing congestion. They allowed people to spread out horizontally before they began to move vertically. Without them, thousands of people entering through different arches would have collided at the foot of a few common staircases. The Romans, however, divided these flows. Structurally, they were true masterpieces. The arches of the corridors were made of Roman concrete, which allowed them to support the weight of thousands of people in the upper tiers. The corridors were wide enough to allow oncoming streams of people to pass freely, although the system was designed to minimize such intersections. Each tier had several such circular corridors. The outer corridor served as the entrance and exit to the building. The inner corridors, located closer to the arena, provided direct access to the stairs leading to the spectator rows. This multi-layered design was the key to its efficiency. This system also played an important role in social segregation. The corridors on the lower tiers, intended for senators and equestrians, were wider and better decorated. The corridors on the upper tiers, where the poor were directed, were simpler and narrower. But the principle of horizontal distribution worked at all levels. These long tunnels were lit through openings in the arches facing the outside of the building. This created a play of light and shadow, but it was sufficient for people to find their way around freely. The floor was paved with sturdy stone slabs capable of withstanding the flow of thousands of feet. The engineers had calculated everything. The location of the vomitoria leading into these corridors and the staircases leading out of them was not accidental. It was optimized so that the flows did not intersect and create congestion. It was a real transportation system within a single building. Even today, when you walk through the wide concourse or foyer of a modern stadium surrounding the arena, you are walking in the direct footsteps of the Roman Annular corridor. The Romans understood that crowds must first be distributed horizontally and only then vertically. This principle remains unshakable. Without these wide horizontal arteries, the vomitoria would have been useless. They would simply have led people into narrow block spaces. It was the combination of vomitoria and ring corridors that created the very system of continuous flow that so impresses us today. In the next chapter, we will see how the Romans moved thousands of people from these horizontal arteries to their vertical destinations. Once the spectator had entered through their vomitorium and reached the correct ring corridor, they had one last step to take: climbing up to their row. This was achieved by a third key system: countless staircases, or scalaria. But here, too, Roman engineers applied their main principle: the separation of flows. The amphitheater did not have a single set of main stairs leading from the bottom to the top. Instead, there was a complex, almost labyrinthine network of multiple staircases. Each staircase served only its own small sector. The staircases leading to the lower, honored rows were completely separated from the staircases leading to the upper, common tiers. This was done for both convenience and social control. The staircases intended for senators and equestrians started directly from the lower ring corridor. They were gentle, wide, and led directly to the best seats at the arena itself. These passages were often hidden from the eyes of the general public, providing the elite with private and quick access. The stairs for ordinary citizens were arranged quite differently. Numerous but narrower staircases led up from the ring corridors of the middle tier. They branched out like the crown of a tree, leading people to different rows within one large sector. It was impossible to use these stairs to enter a sector intended for another class. The engineers created a real three-dimensional puzzle. The circular corridors provided horizontal movement, and the staircases provided vertical movement. But the key was that these systems were not unified, but segmented. The building was divided into many independent cells, each with its own entrance, corridor, and staircase. When we look at the ruins of the Colosseum today, we see only the remains of this complex network. Many spans have collapsed, exposing the internal structure. But even in the ruins, we can trace this ingenious logic of separated flows, which was the main secret of controlling a crowd of 50,000 people. What if I told you that your ticket to a modern match was invented by Roman engineers to control society? The amphitheater's spectator bowl, or cavea, was not just a set of seats, but a sophisticated architectural system that reflected the strict hierarchy of Rome. Every element of this space was designed so that spectators understood which social group they belonged to and where exactly they should sit. Architecture served not only convenience, but also the maintenance of public order, as Rome sought to control its citizens even during celebrations. A person's place in the amphitheater became an extension of their status in everyday life, emphasizing the immutability of the social structure. The entrance system was so carefully constructed that each visitor inevitably ended up exactly where they were supposed to be. The spectator seats were divided into several main tiers, called menians. The lowest and most prestigious tier, the Ima Cavea, was located directly at the arena, where the most intense and vivid events took place. The wide marble benches, often decorated with the names of their owners, were occupied by representatives of the senatorial class, who constituted the top of the Roman elite. Separate entrances were built for them so that they could enter the amphitheater without encountering the crowd. These passages were spacious, richly decorated, and allowed them to maintain the dignity that corresponded to their position in society. Thus, even the physical movement of senators through the building emphasized their exclusivity. Just above were the seats for the equites, Rome's second most important class. Their positions were also considered prestigious, and engineers provided separate approaches for them so that they would not mix with the common people. These routes were designed so that the equites could quickly take their seats, bypassing the crowded corridors. From these seats, they could watch the games with good visibility and feel that they were recognized and respected. This separation also helped maintain order, as the classes did not mix and create conflicts. The Romans understood that physical distribution in space helped maintain social boundaries. Above them began the media cavea, a huge middle tier reserved for full Roman citizens. It was the most spacious part of the amphitheater, because most of the spectators belonged to this social class. People of different professions and tribes gathered here, and the division into sectors emphasized the diversity of Roman city life. Each sector was associated with a specific group of citizens, which helped to avoid disorder. Most of the public vomitoria and stairways led here, as the flow of people was particularly high. In these places, spectators felt part of a huge but orderly community. Even higher up was the summa cavea, the upper tier, where the poor, freedmen, and foreigners sat. These were the most remote seats in the amphitheater, which could only be reached by long and steep staircases. Those who did not have high status but still wanted to participate in city life and watch the spectacles climbed up here. Access here was difficult, but tickets were the most affordable, allowing even the poorest segments of society to be part of the festivities. The elevation of these seats symbolized the distance between them and the elite sitting at the very arena. Roman architects took into account that the presence of an audience from all walks of life increased the popularity of events. Finally, at the very top, often above the stone rows, there was a wooden gallery for those who occupied the lowest position in the social structure. This gallery, called Magnum Summum in Linnaeus, was built of wood and had standing room or simple wooden benches. The conditions here were the most uncomfortable. The wind, heat, and rain were felt more strongly than in other parts of the amphitheater. Nevertheless, even this space gave people the opportunity to see the games, which made the amphitheater a symbol of accessibility to entertainment. These seats were often occupied by women from the lower classes who were not allowed to sit closer to the arena. In the gallery, everyone felt their place in society, literally physically. The ticket, called a Tessera, was the key to this whole complex system. It was a small token, most often made of clay or bone, which stored important information about the spectator's seat. The Tessera indicated the numbers of the arch, tier, sector, and sometimes the row, which allowed the exact location to be determined. Such a ticket turned the amphitheater into a huge mechanism where everyone had to follow a strictly defined path. People did not wander, but automatically became part of a clearly functioning structure. The Tessera was a tool that not only distributed people, but also emphasized social rules. Upon receiving such a ticket, a person became a participant in a well-oiled logistical machine. They did not think about the route. The architecture did everything for them, guiding them through corridors and stairways to their sector. They entered the right archway, climbed the designated staircase, and ended up exactly where they were supposed to be. The routes were designed so that the flows of spectators did not intersect, which prevented disorder. Every step was predictable and calculated in advance by engineers striving for maximum efficiency. Thus, the spectator became part of a huge human flow, moving according to the laws of architectural logic. This architectural segregation was complete and insurmountable. A person with a ticket to the upper tier could not physically enter the spaces reserved for senators, as the passageways were separated by walls. This established not only order, but also social distance, reminding spectators of the boundaries they could not cross. This made the amphitheater a symbol of order, built into the daily life of the city. Romans became accustomed to seeing society in this form and perceived it as natural. Architecture became a mirror of the social structure. Thus, the amphitheater not only entertained the crowd, but also educated it, showing everyone their place in society. Attending the games became a lesson that reminded people of the difference between social classes. People saw those who sat above or below them and understood their position in the Roman world. This visual and spatial structure reinforced the social hierarchy without words. The Romans got used to the idea that order had to be maintained everywhere, even at a festival. This made the spectacles an element of state governance. This ingenious system, involving tickets, vomitoria, corridors, stairways, and sectors, was the main mechanism for controlling huge crowds. It turned tens of thousands of people into an organized flow that moved along predetermined routes. Every person entering the amphitheater became part of a carefully planned movement. Thanks to this, engineers were able to ensure safety and avoid stampedes, which was extremely important with such large gatherings of people. This architectural solution was centuries ahead of its time. The Romans proved that crowds could be controlled not only by force, but also by space. But how did engineers solve the problem of the scorching sun for tens of thousands of spectators? We will find out in the next chapter. Crowd control was not the only engineering problem. 50,000 people sitting for hours under the scorching Roman sun would turn any spectacle into an ordeal. Roman engineers found a strikingly bold and elegant solution to this problem: the Valerium. It was a giant fabric awning or canopy that stretched over the spectator seats. This structure was a true marvel of engineering. The Valerium was not a single piece of fabric, but a complex system of many linen or canvas panels. They were sewn together and supported by a network of strong ropes. In the center, there was a large open hole, the compluvium, which provided ventilation and lighting for the arena. To support this gigantic structure, 240 tall wooden masts were installed along the upper edge of the Colosseum's outer wall. These masts were inserted into special stone brackets, which are still visible on the upper tier of the amphitheater. Ropes converged from the mast to the center, to which the fabric panels were attached. Controlling the Valerium was such a complex task that it was entrusted not to ordinary workers, but to professionals. This was done by specially trained sailors from the Imperial fleet based in Miseno. Only they had the necessary skills to work with ropes, blocks, and sails at such heights and on such a scale. The system worked on the principle of ship rigging. Using a complex system of winches and blocks located on the ground around the amphitheater, sailors could unfold or fold the awning depending on the weather. This made it possible to quickly shelter spectators from the sun, or conversely, to remove the awning during rain so that it would not sag under the weight of water. The unfurling of the Valerium was a spectacle in itself. Hundreds of sailors working in sync as if on the deck of a huge ship pulled on the ropes, and the protective canopy slowly unfolded above the heads of thousands of spectators. The noise of the blocks and the creaking of the ropes was a familiar sound before the start of the games. The fabric for the Valerium was most likely linen, as this material was durable and relatively light. Perhaps the canvases were dyed in different colors or even painted, creating a colorful sky above the spectators. This added to the spectacle and emphasized the wealth and power of the organizers of the games. The very fact that the Romans were able to design and, more importantly, regularly operate such a movable roof is astonishing. It required precise calculations of the wind load, the weight of the fabric itself, and the strength of all elements. Any mistake could have led to the collapse of the structure onto the heads of the spectators. The Valerium did not cover the entire arena, only the spectator rows. This created comfortable shade for the audience, while the arena itself remained brightly lit by the sun. It also created a powerful airflow. Hot air from the arena rose up through the central opening, drawing air from under the awning and creating natural ventilation. This system was the pinnacle of engineering, combining elements of architecture, shipbuilding, and mechanics. It demonstrated that Roman engineers could solve not only static problems, such as building walls, but also complex dynamic ones, such as controlling a giant movable canopy. Thus, the comfort and safety of spectators was ensured not only on the ground and in the corridors, but also in the air. The Valerium was an integral part of the amphitheater, as important as the vomitoria or stairways. The construction of such a colossal structure as the Colosseum was not only an engineering feat, but also an incredible logistical feat. Before the first spectator could enter the vomitorium, millions of tons of building materials had to be delivered to the site and processed. Managing this flow of resources was a task comparable to supplying an entire army. The main material used for the exterior cladding and supporting columns was travertine. This is a durable and beautiful limestone tuff that was quarried in the city of Tibur, modern-day Tivoli, located 30 kilometers from Rome. It is estimated that more than 100,000 cubic meters of this stone were used in the construction of the Colosseum. Transporting these giant blocks was an epic undertaking in itself. Stone blocks weighing several tons were first transported from the quarries to the Annular River. There they were loaded onto barges and floated down to the confluence with the Tiber, and then up the Tiber almost to the very center of the city. From the pier, the blocks were transported to the construction site on huge wooden carts pulled by dozens of oxen. But travertine was only the visible, ceremonial part. The heart of the building, as we already know, was Roman concrete. 3 components were required for its production: lime, volcanic ash pozzolan, and aggregate crushed stone. All of this had to be delivered in huge quantities. Lime was burned in kilns, ash was brought from outside the city, and rubble from other buildings was often used as aggregate. The third important material was tuff, a softer volcanic rock that was used for interior walls that did not bear the main load. It was easier to extract and process than travertine. Bricks were also used, especially for creating arches and lintels, which served as a framework for pouring concrete. Metal deserves special mention. The Romans used thousands of tons of iron staples to fasten the travertine blocks together. The blocks were drilled, and molten lead was poured into the holes, which firmly fixed the staples in place. It is the absence of these staples, which were barbarically broken out in the Middle Ages for remelting, that gives the Colosseum its characteristic porous appearance today. All this massive materials required thousands of workers. Not only slaves were involved in the construction, performing the heaviest unskilled work of transporting and lifting loads. The core of the builders consisted of experienced engineers, architects, masons, carpenters, and decorators. The Romans used complex wooden cranes to lift heavy stone blocks to a height. These mechanisms were driven by large squirrel wheels, inside which people walked, using their body weight to rotate the winch. This allowed them to lift multi-ton loads tens of meters high. Construction proceeded at an incredible speed for that time. The entire Colosseum was built in less than 10 years, which testifies to the highest level of labor organization. Work was probably carried out simultaneously on many sections. Different teams were responsible for their own sectors, which echoes the principle of sectoral division of the building itself. This gigantic construction project was in itself a demonstration of power and wealth. The Flavian emperors showed that they could mobilize enormous resources for a single project. The logistics behind the construction of the amphitheater were as miraculous as its architecture. The ingenious solutions found in the construction of the Colosseum did not remain unique to the capital. They became the gold standard, a successful and proven design that was then replicated throughout the vast Roman Empire. The Romans were masters of standardization, and their amphitheaters are a vivid testament to this. In almost every major city, from Britain to Syria, you can find the remains of amphitheaters built according to the same basic principles. Local architects took the capital's model as a basis and adapted it to local conditions, materials, and scale. But the essence of the crowd control system remained unchanged. Take, for example, the amphitheater in El Jem in modern-day Tunisia. This building is almost as large as the Colosseum and could accommodate about 35,000 people. Its internal structure, although less well-preserved, clearly shows the same system of circular corridors, vomitoria, and separate staircases. Another magnificent example is the Arena di Verona in northern Italy. This amphitheater is so well preserved that opera festivals are held there today. Its internal access system is virtually intact. Visitors still enter through numbered arches and climb the same stairs as the Romans did 2,000 years ago. In the city of Pula, in modern-day Croatia, there is an amphitheater whose outer wall is almost completely preserved. Its architecture clearly demonstrates the same principles: arched openings on different tiers that led to the internal system of corridors. This building also had a Valerium and was designed to accommodate more than 20,000 spectators. In France, in the cities of Nîmes and Arles, the amphitheaters are also well preserved. They were built according to the same pattern. In Nîmes, you can still walk through the circular galleries, climb the stone steps, and feel how this ancient crowd control machine worked. This standardization was incredibly practical. It saved time and resources in design. Engineers did not have to reinvent the wheel every time. They had a ready-made, proven, and safe design that only needed to be adapted to the landscape and available materials. It also had ideological significance. Wherever a Roman citizen was, in Rome, Africa, or Gaul, they saw familiar architecture. The amphitheater was as much a symbol of Rome as the aqueduct or the forum. It carried with it the idea of order, power, and a unified imperial culture. The system of vomitoria and ring corridors became the universal language of Roman public architecture. It was scalable. It could be applied to a giant like the Colosseum or to a small provincial amphitheater with 5,000 seats. The principle remained the same: divide and direct. Studying these provincial amphitheaters helps us understand how fundamental and successful the engineering solutions adopted in Rome were. It was not a one-off success, but a proven and replicable technology. Thus, the Colosseum was not just a building, it was a prototype. It set the standard for centuries to come. Its DNA can be traced in dozens of other ruins throughout the Mediterranean, each telling the same story of ingenious management of mass flows. The Roman Empire fell, and its amphitheaters were turned into ruins, quarries, or fortresses, but the engineering principles behind them proved more durable than stone and concrete. When in the 19th and 20th centuries, humanity once again faced the need to build structures for tens of thousands of people, architects turned to Rome for inspiration. If you look at the plan of any modern football stadium, baseball arena, or concert hall, you will see the same Roman design. The names have changed, but the essence remains the same. We still use a system that is 2,000 years old because it remains the most effective. The modern entrances, or gates, numbered on your ticket, are direct descendants of the Roman vomitoria. They are evenly distributed around the perimeter of the building to disperse the incoming crowd. Their main task is to sort the flow of people at the very first stage. The wide foyers or concourse that surround modern stadiums on each tier are our ring corridors. Their function is identical: to receive people from the vomitoria and allow them to disperse horizontally to find their sector. This is where the food outlets and toilets are located, but the basic principle of movement is the same. The stairs leading up or down from the foyer to your spectator rows are our scalaria. Just like in Rome, they only serve small, strictly defined sectors. You cannot use the stairs from Sector 101 to get to Sector 301. This segmentation is a direct legacy of Roman engineers. Our tickets indicating the gate, sector, tier, and row are an exact copy of the Roman Tessera. This personal access system allows us to turn a crowd of 50,000 into a manageable set of individual routes. We simply do this with computers and barcodes, but the logic remains Roman. Even social segregation has not gone away. Modern skyboxes, VIP boxes, and club tiers are analogous to the seats of senators and equestrians. They have their own separate entrances, elevators, and corridors, completely isolated from the ordinary fans in the upper tiers. Architecture still reflects social hierarchy. Modern engineers use computer modeling to calculate crowd flows, but the goals of this modeling are the same as those of Flavian engineers. They seek to avoid congestion, minimize entry and exit times, and, most importantly, prevent panic and stampedes in emergency situations. Without computers, the Romans were able to calculate all this intuitively and mathematically, relying on experience and common sense. They understood a fundamental rule: crowds cannot be restrained, they must be divided into small streams and kept moving. So, the next time you are in a large stadium, remember this: you're inside an architectural idea that is 2,000 years old. You enter through the vomitorium, walk along the annular corridor, and climb the scala. The genius of Roman engineers was not that they built a large building. It was that they built a smart building. They created a machine for controlling people so perfect that we simply copied it, adding steel, glass, and escalators. This invisible but ubiquitous system of corridors and stairways is the main legacy of Roman amphitheaters. It is a triumph of logic and order over the chaos of the crowd, an engineering solution that has truly survived the millennia. We can see that the Roman amphitheater was not just an arena for entertainment. It was a finely tuned mechanism, a machine for controlling tens of thousands of people. Its genius lay not in the height of the walls or the size of the arena, but in the hidden internal circulation system. Roman engineers solved a fundamental problem that is still relevant today: how to ensure the safe and rapid movement of huge crowds of people. Their solution, based on the principles of decentralization, flow separation, and segmentation, proved so successful that it became the global standard. Vomitoria, circular corridors, and separate staircases are the language that the architecture of mass structures still speaks today. These ancient stones teach us that great engineering is not only about materials, but also about understanding human behavior. The Romans did not just create a building, they created a system that predicted, directed, and controlled the actions of crowds, ensuring order and safety. Please suggest topics for future videos that you would like to see on our channel in the comments. We carefully read all your ideas. And of course, subscribe so you don't miss our next explorations of the engineering wonders of the past.